Welcome back to the deep dive. You know that moment in materials science or solid-state physics when you hit chapter 6 and
Mhm.
suddenly the neat, tangible world of atoms and crystal planes just sort of melts away into a sea of asterisks and inverse lengths? We are talking about reciprocal space. If you've been deep in crystallography, you already rely on Miller indices, those
Mm.
theta triplets, to identify every unique plane in your structure.
Mm.
But, and this is the dirty secret, those indices are just symbols. They're static integers.
Right.
They don't mathematically behave like vectors you can use to calculate things like the true distance between planes or the angle between them, especially not in a complicated skewed lattice.
That's the core paradox we are here to solve today. You have a physical object, a crystal, described by three simple integers. But when you try to use that triplet in standard vector math to measure its properties, it simply doesn't work unless your crystal is perfectly cubic. Our mission in this deep dive is to shortcut the anxiety and show you exactly why we need this abstract, seemingly inverted space, and how it fundamentally transforms those three integers into the most powerful, measurable quantity in diffraction science, the interplanar spacing, dog-any-do.
We've taken the source material, chapter 6 of Structure of Materials,
Mhm.
and really distilled the essential relationships. We're going to take you step by step, starting with the immediate problem.
Yeah.
How do we mathematically transform those indices into a usable vector?
Yeah.
We will reveal the core breakthroughs, culminating in the proof that a vector's length in this reciprocal world is the inverse of the physical distance in the real world.
And this transformation from the abstract to the applicable is what makes crystallography a rigorous engineering tool. The chapter opens with a brilliant quote from Theodore von Karman.
Oh, I love this quote.
It's perfect. The scientist describes what is, the engineer creates what never was. Reciprocal space is the mathematical foundation, the what is, that allows materials engineers to precisely analyze and thus create brand new structures, the what never was.
Let's jump straight into the necessity of this concept, starting where the text begins. The need to assign vector properties to Miller indices. So we've used Miller indices to identify any arbitrary plane in the crystal, but we need to do more than just identify them.
Right.
If we want to find the direction perpendicular to that plane, the plane normal, or calculate the distance between parallel planes, we need vector analysis.
Exactly. The challenge lies in interpretation.
Hmm.
We want to treat Kayla not just as symbols defining intercepts, but as the genuine components of a vector, let's call it math BFG, that is normal to the plane.
Okay.
The moment you try to use abricular neural Taylor and dollars as components of a vector in the direct space, the space defined by our physical unit cell basis vectors, mass BFA3, mount BF3, the mathematics immediately falls apart.
Unless the lattice is cubic.
Unless it's cubic, then you get lucky.
But why does it fall apart? If I try to define a vector, say math BFG plus math BFC plus math BFC phi, and then try to find a vector math BFEB lying in the neoscalar plane such that their dot product is 0, which is just the definition of perpendicular.
Right.
That relationship almost never holds true in skewed systems like monoclinic or triclinic.
Precisely. In a non-orthogonal system, the vector defined by the Miller indices in the direct basis, math BFA phi plus math BF is not guaranteed to be perpendicular to the plane layer.
Okay, so the coordinate system is the problem.
The coordinate system we use for the physical crystal, the direct lattice, is terrible for spatial calculations involving planes. Since vector components are always taken with respect to some set of basis vectors, and we need a system where the Miller indices, BAC, do define a normal vector.
We have to abandon the one we're used to.
We must abandon the direct basis for this purpose. We need a special related set of basis vectors, one that is geometrically optimized for perpendicularity. This necessity gives birth to the reciprocal space.
It's important to stop and emphasize this difficulty. Reciprocal space is abstract, but it is not arbitrary. It's born out of necessity. It's the mathematical bridge that fixes the geometry problem, allowing us to connect the abstract description of the crystal lattice to the measurable physical results of diffraction experiments. Without this space, the analysis of anything non-cubic is, well, mathematically intractable. All right, so we need a new coordinate system. Let's look at how the textbook defines the basis vectors for this new space.
We introduce a new set of basis vectors denoted math BICE, where that asterisk signals that we are in the reciprocal space. Now, while the choice of the unit cell basis vectors in the direct space, math BIA2, math BIA3, is somewhat flexible,
Right.
we choose the reciprocal set for maximum mathematical convenience and symmetry. We impose a highly specific, very restrictive relationship between the direct vectors and these new reciprocal vectors.
And this is the core definition.
Here is the defining relationship, the key to unlocking the entire space, captured by the Kronecker delta property.
Okay, that formula looks a little intimidating if you aren't fluent in tensor notation, so let's break down the implications of that Kronecker delta, delta L.
Kronecker delta is actually pretty simple. It's just a mechanism to enforce specific orthogonality and scaling rules. The result of that dot product, math BSS, must equal 1 when the indices, all are the same, and 0 when they are different.
So it's like a switch, on or off.
Exactly. Let's look at the first reciprocal vector, math BSS. If we use I01 and then let Jappy be 1, 2, and 3, we get 3 conditions.
Okay.
1, math BSC, that's the scaling condition. 2, math BSE, that's an orthogonality condition. And 3, math BFC, math BSE, that's an orthogonality condition. And 3, math BFC, the second orthogonality condition.
Wait, let me make sure I grasp the physical constraint here. The requirement that the dot product of math BFC RC 10 NEFC must be 0. That means that math BFC has to be perpendicular to both math BFC and math BFC.
Precisely. And if a vector is perpendicular to 2 other vectors, what do we know about its direction?
It has to be parallel to the plane defined by those 2 vectors.
Mm-hmm.
Or, well, perpendicular to the plane they define. So it must be parallel to their cross product, math BFC play.
You've got it. That's the direction sorted. We've defined the direction. Math BFC has the same direction as Math BFC 10ET. The next step is just nailing down its magnitude.
The scaling.
Yes, we know Math BFC must be proportional to Math BFC, so we can write Math BFC where K is just some scaling factor.
And we find K using that last piece of the definition, the A dot A star equals 1 part.
Right. We substitute our cross-product relationship into that equation. Math BFC, Math BFC, Math BFC, poo is 1.
And K is a scalar, so you can pull it out front?
Yep. So we get KK Math BFC, AFC. And this is where the geometry of the entire unit cell comes into play. That term in the brackets, Math BFC, is the scalar triple product.
Which is the volume of the unit cell, volume V.
Exactly. So we substitute V for the scalar triple product, and we get KKOV equals $1. That forces the proportionality constant dollar to be a level dollars.
Ah, so the volume of the direct unit cell is the explicit scaling factor that governs the size of the reciprocal basis vectors. That's incredibly elegant.
Isn't it? It links the definition of the reciprocal basis directly to the fundamental physical scale of the crystal unit cell.
So that means if we have a huge unit cell, a large V for our direct lattice, our reciprocal basis vectors will be very small, because they're scaled by $50.
That's why it's called reciprocal space. It's inversely proportional.
It reinforces the name.
And that's the intellectual payoff. This derivation gives us the explicit forms for all 3 reciprocal basis vectors. Math BSC is Math BSE and Math BFCDS, and Math BSC is Math BFC, and Math BFC is Math BFC. Math BFC will go to the new basis for the reciprocal lattice.
And this confirms that we haven't created some separate reality, just a highly optimized coordinate system. The text points out that any physical vector math BFC can be described either by its direct components or by its reciprocal components.
It's the same vector, just viewed through different geometric lenses.
Which is where that conceptual walkthrough in the text about the monoclinic lattice becomes so important.
It really does. Remember that in a monoclinic system, one angle, let's say beta, is not 90 degrees, but the other 2 are. This means that Math BFC and Math BFC are not perpendicular.
Right. The unit cell is skewed.
Precisely. If you calculate the reciprocal vectors for this monoclinic case, say with parameters 1, 1, 1 and angles 90, 45, 90, you first have to determine the volume V using that $45 circ angle. Then, when you apply the cross-product formulas, you realize something interesting.
What's that?
Math BF is not parallel to Math BFC, and Math CS is not parallel to Math BS.
Wait, if the reciprocal vector math BFC isn't parallel to its direct counterpart math BS, doesn't that make the reciprocal cell itself highly skewed in a different way?
It does. That's the beauty and the difficulty. In reciprocal space, the geometry, the angles and lengths are inverted and warped compared to the direct space. Unless the direct space is already perfectly orthogonal, like in cubic or orthorhombic systems, the reciprocal basis vectors are forced to satisfy those Kronecker delta conditions, meaning Math BS must be orthogonal to Math BS on math, but if Math BFC define a skewed direct plane, the vector perpendicular to that plane might be pointing somewhere totally unexpected relative to Math BFC.
So the monoclinic example proves that while the direct basis vectors define a simple parallelogram, the reciprocal basis vectors required to enforce the perpendicularity constraint form a much more complex, non-intuitive parallelogram. Yet they mathematically hold the key to simplifying plane geometry. We have established the new coordinate system. So the next logical question is, how do we use these new basis vectors to define the specific thing we care about, the plane normal?
This is where we define the specific vector of interest, the reciprocal lattice vector, math BFG. We define math BFG by restricting its components to be integers when expressed in the reciprocal basis, plus k math BFG or plus LFG have to be integers.
Crucially, out TK and LO dollars must be integers. The collection of all possible vectors, math BFG, that satisfy this integer restriction forms what we call the reciprocal lattice.
And since we are restricting the components to integers, these vector components are now formally the same as the Miller indices.
Exactly. Okay, that's the mathematical setup. We finally converted the abstract integer triplet, scalar, into the components of a mathematically rigorous vector, math BSKLL. Now we need the payoff. What does this vector physically represent?
This is the absolute geometric triumph of the reciprocal lattice. This is the single most important conceptual result. The reciprocal lattice vector, math BFKO, is perpendicular to the corresponding direct lattice plane.
So it is the normal vector we've been looking for.
It is the normal vector, and the proof is really neat. Consider a plane in direct space defined by the Miller indices, HA Aldol. We look at a parallel plane that passes through the origin. Any vector math BFG lying in that plane can be expressed as a linear combination of two other vectors in that plane.
And we know that if the vector math BFG is normal to the plane, then the dot product of math BFG and any vector math BL lying in the plane must be 0.
Math BFD. Precisely. If we substitute the general forms for math BFGR and for math BFG, and we use the beautiful simplification provided by that Kronecker delta relationship we talked about.
The one that makes most of the terms go to 0.
Right. Yeah. The condition math BFG, or COT-G, simplifies down to an equation involving Galler K and the components of math BFG. When you look at the final form of that equation, you realize that the components $TIG, a dollar in the vector math BFG, must be the reciprocals of the plane intercepts of the original lattice plane.
Which, by definition, is exactly what Miller indices are.
That's it. By creating the reciprocal basis, we mathematically forced the vector composed of the Miller indices to be the vector normal to the plane defined by those indices.
This resolves the central geometric difficulty of crystallography. Before, we had to rely on geometry and, visualization to find the plane normal. Now you just plug the indices into the reciprocal basis, and the math automatically gives you the vector pointing in the correct perpendicular direction.
Doesn't matter if your crystal is cubic or monoclinic or what have you.
To visualize this, imagine that highly skewed monoclinic unit cell again. You draw the plane, $102, which slices through the A-axis at $1 and the C-axis at $12. Because the angle BA is, say, $45, the line normal to that plane is not simple to predict geometrically. But the reciprocal vector, math BFG, which starts at the origin and ends at the coordinates, $, is $2 in reciprocal space, is guaranteed to be pointing in the exact direction of that normal. The reciprocal lattice point, HA caret, represents the endpoint of the normal vector for the HA plane.
This perpendicularity makes the reciprocal lattice indispensable. It converts a complex geometric problem defining a plane normal in a skewed reference frame into a simple problem of defining a vector using integer components in a highly optimized reciprocal frame.
Okay, so we've established the direction of the reciprocal vector math BFG. That's half the normal. The other critical piece of information we need is its magnitude, its length.
Right.
Knowing the direction is useful, but we need the length to determine the interplanar spacing.
To compute lengths and angles accurately in this non-orthogonal reciprocal space, we need a mathematical tool that captures the geometry of the space itself. We introduce the reciprocal metric tensor, math BFG.
So the metric tensor is like a geometry map.
It's a perfect analogy. Think of it as a universal translator for geometry. If you're trying to calculate the distance between 2 points on a flat, simple Cartesian grid, you use the Pythagorean theorem. It's easy.
Right.
But if your coordinate system is severely skewed, like measuring distances on a diamond-shaped or parallelogram-shaped grid, standard Pythagorean addition fails. You need a correction factor to account for the skewness. The metric tensor provides that correction.
So if the direct cell is simple, like cubic, the direct metric tensor math BFG is simple. And if the reciprocal basis vectors math BFGs are non-orthogonal, the reciprocal metric tensor math BFG will be complex.
Exactly. The components of the reciprocal metric tensor are explicitly defined by the dot products of the reciprocal basis vectors. And this lets us calculate length.
Right. Since the length of any vector math_BFG is the square root of the dot product of math_BFG with itself, the tensor math_BFG ensures that this calculation correctly incorporates the reciprocal cell's geometry. The equation involves multiplying the indices KSGA by the math_BFG matrix and then by the transpose of the indices.
This allows us to calculate the true physical length in a skewed space using simple matrix multiplication. I think it's worth pausing here to discuss the structure of these tensors for the different systems.
Let's look at the extremes. For the cubic system, the direct basis vectors are all perpendicular and equal in length. This means the reciprocal basis vectors are also perpendicular and equal in length.
So math_BFG is simple.
Very simple. The math_BFG matrix is just a diagonal matrix with terms like 100 to 2 all along the diagonal. All the off-diagonal components are 0. The off-diagonal terms, where is such a day, they represent the angle relationships, right? So if they're 0, it means the axes are orthogonal.
Correct. But now consider the triclinic system. In triclinic, none of the direct axes are perpendicular and none of them are of equal length. This massive non-orthogonality in direct space means the reciprocal basis vectors are also highly skewed relative to each other.
Meaning the tensor is not simple.
As a result, the math_BFG matrix is a full $3 times 33 matrix where every single component G12, all of them, is non-zero and complex. The off-diagonal terms, like G12es, capture the geometric coupling between the math_BFG that arises from the skewed geometry.
That's the power of it. The metric tensor carries all the geometric burden. If you know the direct lattice parameters, you can compute the tensor math_BFG. Once you have it, calculating any length or angle in that crystal becomes a routine, systematic matrix operation, no matter how complex the crystal structure is.
And the text also notes that math_BFG is mathematically the inverse of the direct metric tensor, math_BFG.
Okay, let's look at the first application. Finding the angle between two planes, say h kilowall.
Right.
Since we established that the reciprocal vectors are the normals to the respective planes, finding the angle between the planes is just finding the angle between those two vectors.
We rely on the standard definition of the dot product. Math_BFG, math_BFG, math_BFG. So we just rearrange for cosine theta.
Exactly. We said their dot product divided by the product of the lengths. The crucial step is that both the dot product in the numerator and the lengths in the denominator must be computed using the reciprocal metric tensor math_BFG.
So that we're accounting for the skewed space.
This ensures that even if we are finding the angle between two plane normals in a monoclinic crystal, the resulting angle theta is the true physical angle. It transforms what would be an agonizing exercise in solid geometry into a systematic calculation.
So the complexity is hidden inside the tensor. It is. When you examine the explicit cosine expressions in Table 6.2 of the text, for cubic crystals, the formula is almost trivial. But for triclinic or monoclinic crystals, the formula becomes monstrous. The tensor handles that complexity so you don't have to.
Now for the ultimate relationship. We have the direction. We have the framework for calculating length. We need the final link that connects this abstract length back to a physical, measurable property.
We return to the magnitude of math_BFG. As the text shows, you can derive the length by examining the perpendicular distance from the origin to the plane.
Right.
After the full trigonometric and vector derivation is completed, a process that explicitly uses the perpendicularity we established earlier, we arrive at the defining relationship between the two spaces. And this is the big one.
Let's hear it.
The length of a reciprocal lattice vector math_BFGO is exactly equal to the inverse of the interplanar spacing direct of the corresponding direct lattice planes. Math_BFGO 1 DSGO.
This is the critical physical link. This is the payoff. The abstract geometry of reciprocal space is now tied directly to the most critical physical measurement in diffraction. In X-ray diffraction, Bragg's law shows that the scattering angle is determined entirely by Dibble game. By measuring the angle, we can calculate deladone, but now we know that calculating one deladu is the same as calculating the length math_BFXU using the reciprocal metric tensor. This means diffraction measurements are essentially measurements of the lengths of reciprocal lattice vectors.
That's it, exactly. We convert a physical measurement, an angle of scattered X-rays, into a geometric measurement, the length of a vector in reciprocal space. The entire X-ray diffraction pattern is simply a map of the reciprocal lattice.
Which is why the concept is so foundational.
It is, Because of this inverse relationship, the complex formulas for calculating the length math BFG using the metric tensor are mathematically identical to the formulas for calculating $1. Table 6.1 in the text is effectively the instruction manual for finding the length of math BFG for any crystal structure.
Theory solidified. Now let's conceptually walk through the 3 computational examples in the textbook to see the math BFG tensor in action. The goal here isn't to do the arithmetic, but to understand how the tensor acts as our geometric translator.
We start with the simplest case, a cubic crystal, where ABC and all angles are $90. Let's find $1 for a lattice parameter H dollars.
Okay, so the system is cubic, which means the math BFG tensor is maximally simple, just diagonal.
Right, with components of 1 and 2. The vector math BFG10 is represented by the column matrix $1, $1, T2. Since the system is orthogonal, the calculation is very straightforward. The general formula for the squared length math BFG2 simplifies right down to H dollars plus K2 plus L2 A22.
And that simplification is only possible because the off-diagonal terms of math BFG is 0.
Correct, they don't contribute. For $110, we get math BFG2, 12 plus 12 plus O2, 22.2, which is 24.3, or $7.55. Taking the square root, math BFG10 is about 0.707 or 11. Since D10 is the inverse of this length, it comes out to about 1.414 times the lattice parameter.
The tensor method works quickly and cleanly, confirming the well-known geometric result.
This example is important because it shows the tensor is universally applicable, even when the geometry is simple. The matrix system automatically collapses into the familiar Pythagorean result.
Now let's go to the nightmare scenario. Triclinic. This is the system where no axes are equal and no angles are 90 sorting. This calculation would be a geometric torment if you tried to do it in direct space.
It would. The goal is to find a complex triclinic crystal. The textbook uses parameters like A33 lattice, B4, C6x's with angles 90, 90, 120, a highly skewed arrangement. The vector math BFG is $1, $123, $12.
The conceptual method here must be way more involved.
It is. There are 3 massive computational steps before we even calculate the length. First, you have to calculate the complex unit cell volume, $5. Second, you have to calculate the reciprocal basis vectors themselves using those cross-product formulas. And third, you have to compute every single component of the math BFG S metric tensor using the dot products of those complex reciprocal basis vectors. Because the direct space is skewed, the reciprocal basis vectors are also non-orthogonal and complicated.
Meaning math BFG is full of those critical non-zero off-diagonal terms.
Precisely. Those off-diagonal terms, like G12 east, are mathematically essential here. They encode the fact that the axes are coupled geometrically. If we ignored them, our distance calculation would be wrong.
So the tensor method is really the only systematic way to do this.
It is. You simply input the components $1, $100, $100, and multiply by the dense $3 times 3 matrix. The tensor absorbs all the complexity of the geometry, the 120th circle, the differing side lengths, and just outputs the squared length.
And the numerical result in the example, $80 on, demonstrates that even the most complex geometric calculation is reduced to a standardized matrix operation. This transformation is why crystallography is manageable today. Our final example switches from distance to angle, and we are back in the monoclinic system where one angle, the entity delay, is not $90.
Goal. Find the angle theta plane between the normals to the 101 and 2-1 planes. Let's assume typical monoclinic parameters, BFC6 to C55 and beta 120 circ.
So we have 2 vectors, math BFG and the math PSC.
Right, math BFG1 is $1, $1 and math BFG is $2, $1. Now, since beta is not 90 turns, the math BFG is tensor for monoclinic systems will have off-diagonal elements in the amaze plane.
This is a subtle but important point. The off-diagonal terms are only present where the direct basis vectors are non-orthogonal. So in monoclinic, math BFE is not orthogonal to math BSC, but math BFP is orthogonal to both.
That's precisely right.
So that means G12 east are 0, but G13 east is non-zero. The tensor structure tells you exactly which axes are coupled geometrically.
Correct. So step 1 is the computation of the dot product, math BFG doubletitudno. We perform the matrix multiplication using the monoclinic math BFG a tensor, and this implicitly uses those non-zero components to correct for the 120 tons circ skew.
Then you find the length of each vector separately.
Step 2. Compute the length of each vector, again using the tensor. This gives us the normalization factors. And step 3, plug those values into the inverse cosine function. The math is detailed, but the process is standardized. The calculation yields the specific angle, which in this example is $130.25.
What's powerful here is that we found the true angle between two planes in a highly skewed crystal system, using simple integer indices and a universal matrix. The reciprocal metric tensor is the tool that standardizes all spatial measurements for any crystal structure. We've survived the mathematics. Let's zoom out and appreciate the intellectual journey that made these tools possible. It's important to remember that this wasn't just invented to solve a current problem. That's right. We turn our attention to Paul Peter Ewald, 1888 to 1985. Ewald, a German crystallographer, conceived of the geometric concept of the reciprocal lattice in 1912. Think about that date, 1912. That's before Max von Laue published his discovery of X-ray diffraction patterns later that same year. Ewald was developing the mathematical tools for a physical phenomenon that hadn't even been observed yet.
It's an incredible story of pure mathematical abstraction preceding physical discovery. Ewald was studying the interaction of light waves with an idealized crystal lattice. He realized that to describe wave scattering efficiently, he needed a periodic lattice representation where the distance between points was inversely related to the distance between planes in the real crystal.
He literally invented the space because the math told him it had to exist.
It did. His abstract concept became the standard geometric precursor to the interpretation of Bragg's law. Ewald's construction, the Ewald sphere, which we use today to visualize diffraction conditions, relies entirely on the geometry of the reciprocal lattice.
He described what the geometry must be, and then physics caught up. This brings us back to Theodor von Karman, 1881-1963, whose, quote, set the stage for this deep dive.
Von Karman, a true prodigy, spanned fields from fluid mechanics to aeronautics. He was instrumental in applying rigorous theoretical mechanics to tangible physical problems.
The application of the abstract.
Right. And we can now revisit his quote. The scientist describes what is. The engineer creates what never was. Ewald described the mathematical what is, the precise geometry of the reciprocal lattice, which proved to be the exact framework needed to analyze X-ray diffraction. This analysis allows material scientists to characterize existing structures and intelligently design new ones.
Effectively creating what never was.
Exactly. The theory of reciprocal space transitioned from pure math to the bedrock of modern materials engineering.
It's the perfect illustration of abstract theory having immediate, profound physical consequences. We wouldn't have modern solid-state physics or materials science without Ewald's leap of faith into a purely geometric, reciprocal world. Okay, let's unpack this. We navigated the most abstract, yet arguably the most necessary territory in crystallography. Reciprocal space. If you felt overwhelmed by the formulas at first, just remember the three fundamental takeaways.
First, remember the mathematical definition of the reciprocal basis vectors, math BFCSE. They are defined by that clean, simple Kronecker delta property. This construction ensures that the reciprocal system is perfectly optimized for describing planar geometry.
Right, even if the reciprocal cell itself is highly skewed. Second, the fundamental geometric link. The reciprocal lattice vector, math BFTL, whose components are the Miller indices, is always perpendicular to the corresponding direct lattice plane.
This means that the simple coordinate of a point in reciprocal space is the direction of the normal for the plane in real space.
And third,
the critical physical link. The length of that reciprocal vector, math BFPSCL, is the inverse of the interplanar spacing tensor. This relationship, coupled with the power of the reciprocal metric tensor, converts complex geometric problems in real space into standardized matrix calculations in reciprocal space.
These relationships are not just theoretical curiosities. They simplify the analysis of X-ray diffraction data enormously, making it possible to determine the structure of any crystal, from the simple cutic to the impossibly complex triclinic. You now have the shortcut to understanding the geometry that makes materials science possible.
Here's a final provocative thought for you to explore, one that ties back to Ewald's work. Go look up the Ewald sphere. That construction is the standard way we visualize diffraction in 3 dimensions. Now that you understand that every reciprocal lattice point represents a plane, normal, and nulli spacing, ask yourself this.
Go on.
How does the geometric condition of a wave striking that sphere, a purely geometric structure in reciprocal space, translate into the physical conditions necessary for Bragg reflection to occur? The geometry we discussed today is the engine driving that entire process.
That is a perfect challenge to leave with you. Thank you for joining us on this deep dive into the heart of crystal structure analysis. We hope you now see the asterisk not as a symbol of confusion, but as the key to a beautifully ordered mathematical world. We'll catch you next time.